In this lecture, we will talk about the systematic approach to model building. After this lecture, you should be able to describe a process model and its uses, understand the model development cycle, explain the elements in mathematical model, classify the types of equation and variables in process models, and discuss the general procedure and techniques for process modeling. Before we start learning how to develop process models, it is worth considering what a model actually is. Here are two quotes by eminent thinkers of their time. Plato described nouns as being models of events, processes, or ideas. Stephen Hawking stated that a good model or theory needs to describe accurately a large class of observations and make definite predictions about future observations. Expanding on that, a mathematical model is a description of a physical process in mathematical terms, based on empirical observations or experiments. There is a wide variety of physical phenomena. I have listed a few examples here that can be measured. These measurements are called observations, and these are used to develop understanding of the processes and often results in physical laws, which are mathematical statements about a fundamental part of a system that are always true, or always true under some conditions. For example, we don't need to worry about quantum mechanics to calculate the flow of fluid through a pipe, but we may need quantum mechanics to calculate physical properties of materials from first principles. Having analyzed the measurements and developed a model of a system, we should be able to use this model to make predictions of future experiments. Often, we call these simulations. We can then compare these predictions with real experiments and validate the model, meaning we confirm that the model is predicting what would happen in the real world with sufficient accuracy. What processes can be modeled? Any phenomenon that can be described mathematically. In principle, we could model anything, but in practice, we might have to make some simplifications. For example, we know the laws governing the motion of molecules in a fluid, but we cannot practically use that to work out the flow patterns of fluid flowing through a pipe or piece of equipment. We use a more practical approach. In this unit, we will consider modeling processes using physical phenomena that you have already learned. Okay, so chemical reactions, both homogeneous and heterogeneous systems, flowing fluids through equipment, with or without reactions, heat transfer in solid bodies and between fluid interfaces, mass transport from a fluid phase to a surface, and dissolution of solids. As I have emphasized in our last session, I expect you to already know these topics as you have already covered them in your other modules. Please revise your notes for these modules if you think you don't remember them very well. What you will learn from this module is very important for your chemical engineering careers. According to the Institution of Chemical Engineers, it is not plausible today to produce a chemical engineer who is not fluent in the application of computer power to chemical engineering problems. The problems that we normally encounter or face as chemical engineers are complex, and normally require computers to solve them. All chemical engineers need to be competent in process modeling and computer simulations. So mastering this module will give you a competitive advantage in your future careers as chemical engineers. In this module, you will also learn transferable skills that will be helpful for your other modules. In your final year, you'll be doing more reaction engineering. I teach that module, and I can tell you now that what you learn from this module will be useful for that. In your final year design project, you will be required to present a rigorous design of a process, and you need to apply the skills you learn here for that. These skills are also transferable to some other industries such as automotive, petroleum, finance, and so on. There are many uses of mathematical modeling in chemical engineering. Models can help us understand complex systems. Rather than only looking at measurable quantities from experiments, a good model that matches these results can also give us other quantities that are hard to measure, and we can learn more about systems in this way. Models can help us understand what the design and control variables are in a system, what can be controlled and what cannot. Models are very useful in performing sensitivity analysis and optimizing processes. Optimization techniques are also useful for designing experiments to get the most information out of the system for each experiment. Instead of randomly trying different conditions, you work out what conditions to apply to help you improve your model. Lastly, models can be used in research and development, training, and education. Operator Training Simulator, or OTS, are very common in industry to train operators before they run real plants. The advantages of using simulations are obvious. It is much cheaper to run a simulation on a computer than perform a real experiment in the lab or on a pilot plant. However, the models must be validated properly to ensure the accuracy of the simulation and optimization results. The model building process is represented by this diagram. You have already seen the left-hand side. Define the physical process to be modeled. Identify controlling phenomena and modeling goal. Then derive the mathematical equations that meet these modeling goals. Generally, we will need to solve our models numerically because most complex processes do not have analytical solutions. Thus, we apply a numerical algorithm to solve the equations, and this, along with the results management system, for example, plotting graphs, analyzing output data, and so on, constitutes what is known as a computer simulation. At this point, further analysis is needed to estimate parameters for the model and to compare the results with experimental data. If there is a good match, then the model is good enough to use as a simulation tool. Otherwise, you need to identify what phenomena may be missing from the model that is preventing it from matching the data to a sufficient accuracy. You go around the loop until you have a sufficiently accurate model to use as a tool for one of the purposes we discussed on the last slide. In this course, we will be considering the steps up to the computer simulation. We will identify controlling phenomena and derive the mathematical equations. Then, in your numerical analysis lectures and MATLAB sessions, you will learn how to solve the equations numerically. For the mathematical modeling elements, we require knowledge of a number of fundamental laws such as mass, momentum, and energy balances. You have set up many mass and energy balances in your previous modules. Momentum balances are useful in determining pressure drops as fluid flows through equipment. We will also need thermodynamics principles, as well as the rates of mass, momentum, and energy transports. These are needed for the balance equations. These are the rates at which these quantities enter or leave the system or control volume. We will also need the rates of chemical reaction. The body of knowledge and disciplines involved in building a mathematical model for chemical engineering processes is summarized in this diagram. As you can see, mathematics is only one of the components that feeds into modeling of chemical processes. Although not all of these disciplines may be needed for a particular model, you need to be familiar with all of them in order to be a good modeler. The principles from these disciplines will help you understand the systems that you are modeling, which is what's required in order to develop the model equations and interpret the solutions. Don't worry if you initially find modeling daunting, because it relies on having knowledge of many disciplines and putting them all together. You will get better with practice and experience. For the models that we will set up in this module, we will only need reaction kinetics, mass and energy balances, transport phenomena, thermodynamics, and mathematics. This is good news because you already have experience in all of this from your previous modules. However, in your final year design project and in professional practice, you will also need economics, process control, material science, and environmental engineering. When developing a model, it is important to define the boundary of the system, which separates the system from its surroundings. We need to model all interactions among the constituents in the system. We may also need to model the interactions between the system and its surroundings. As you may recall, we define 3 types of system. Isolated, where the system can exchange no energy, momentum, or material with the surroundings. Closed, where no material is exchanged, but the system can exchange energy in the form of heat and work, and momentum, an external force such as gravity, with the surroundings. And open, where material can enter and leave the system, as well as there being interactions in the form of energy and momentum. The balance region, or control volume, is a volume in space over which the balance equations and conservation laws will be applied to derive the mathematical model. The control volume could be the whole system if the system is considered perfectly mixed, as you might do for a batch reactor or CSTR. Models based on this approach are called lumped models. All spatial variations in the system variables are lumped into a single value that represents the average value over the whole system. System variables can be temperature, pressure, concentration, and so on. When the spatial distribution is important, such as in a tubular reactor, we use a differential control volume and derive equations that represent the behavior of the system at points in space. Such models are described as distributed because the system variables depend on spatial position, meaning their values are distributed over space. The mathematical representation of physical phenomena usually takes the form of algebraic or differential equations involving 2 or more system variables. Algebraic equations relate these variables directly. That is, there are no derivatives or integrals. Some examples of algebraic functions are given here: polynomials, logarithmics and exponentials, trigonometric functions, and so on. This type of equation usually defines things such as heat or energy flows or fluxes, rates of reaction, and so on. Differential equations relate the rates of change of one or more of the system variables. That is, there are derivatives with respect to space or time. Many mathematical models include differential equations because they are based on fundamental physical laws which relate rates of change. Lastly, whether algebraic or differential, equations can be classified as linear or nonlinear. If variables and derivatives all appear alone in each term of the equation raised to the power of 1 and not inside any nonlinear function, then the equation is linear. This is important because linear equations are easier to solve. Nonlinear equations, therefore, break at least one of these rules. Examples of nonlinear functions are given here: log x, x times y, the square of a derivative. Here, we have some specific examples of linear or nonlinear differential and algebraic equations. Differential equations can be classified according to the number of derivatives with respect to different independent variables. Ordinary differential equation for just one independent variable. Partial differential equation for more than one independent variable. Variables can also be classified as independent or dependent, which we have briefly touched on already. Independent variables do not depend on any other variable in the system. They are usually time and spatial coordinates. Dependent variables depend on one or more independent variables or other dependent variables. For example, the temperature may be a function of time and spatial position. In this example are ρ, the density, Cv, the constant volume heat capacity, and K, thermal conductivity, dependent or independent variables. The answer is, it depends on whether you assume them to be independent of temperature, pressure, and composition or not. Is the equation linear or nonlinear? The answer is linear if ρ, Cv, and K are constant. Note that the second derivative term is a linear term. As we saw before, we can have lumped and distributed models depending on whether spatial variations are taken into account. Variables can be lumped or distributed in the same way. Lumped if they only depend on time. Distributed if they depend on spatial position. We have talked about the types of equations that can be used in a mathematical model, but there are other aspects to a model. First is a clear definition of all variables. It is very important to list all assumptions clearly and include justifications for all of them. Implicit or unjustified assumptions can lead to the model being used in situations that are unsuitable, where the model may not be sufficiently accurate. Input and output variables can also be listed to enable the model user to understand what degrees of freedom they can specify and what the calculated outputs of the model will be. Input variables can be functions of time, for example, inlet flow rate, or functions of spatial position, for example, specifying an inlet velocity profile that varies radially. Other important elements are boundary and initial conditions needed for differential equations. For differential equations with spatial derivatives, you will typically need one or two boundary conditions depending on the order of the equation. One boundary condition for first order, two boundary conditions for second order, because you will get an arbitrary constant each time you need to integrate the equation. Once for first order, twice for second order. Boundary conditions are required to determine these constants. Boundary conditions can be at one end of the domain for first order or at both ends for second order. Differential equations with temporal derivatives also require initial conditions, which are values of the variables appearing in the derivatives at some initial time, usually a time equal to 0. Finally, it can be useful to perform a degree of freedom analysis on the model to determine how many independent specifications can be made in order to solve the equations. As well as determining how many degrees of freedom there are, it is useful to define which sets of variables are sensible specifications. Now, I have some exercises for you to try. First, look at this equation for three-dimensional heat conduction. Try to identify what the independent variables are and what the dependent variables are. There is a hint already on the slide. Is the equation linear or nonlinear? And is it an ordinary differential equation or a partial differential equation? Pause the video now and restart it once you have an idea of what the answers are. So, did you get them all? First, the only dependent variable is the temperature. The hint is on the right, that T, temperature, depends on the spatial coordinates x, y, and z, and time t. Then, the independent variables must be x, y, z, and time t. I haven't included k, rho, and cv as they are parameters. Depending on the system, they may be functions of temperature. If appropriate, we can just assume that they are constants. Now, the equation is linear because temperature only appears to the first power in all terms, and there are no functions like sine t or log t. Finally, it is a PDE because there are derivatives with respect to more than one independent variable. In fact, this equation has derivatives with respect to all 4 independent variables. Now, for the next exercise, we will look at heat loss from a rod. The diagram shows that the rod has length L, and there is heat lost to the surroundings at ambient temperature along its length. The ends of the rod at Z equal to 0 and Z equal to L are held at temperatures T1 and T2 respectively. The differential equation below describes how the temperature changes within the rod. Once again, think about what the dependent and independent variables are. Also think about whether this is an initial value or boundary value problem. How many initial or boundary conditions are needed to solve the equation? Pause the video now and start it again when you are ready to compare your answers. Again, the only dependent variable is the temperature T. The ambient temperature, denoted by T subscript amb, is uniform along the length of the rod. It is not written with a Z in parentheses, like the temperature T. which indicates dependence on z. Now, there's only one independent variable, the coordinate z. It is a one-dimensional steady-state model, so only one spatial coordinate and no time dependence. If you said boundary value problem, then you are right. When you have a spatial derivative, you need to specify one or more values at the boundary of the spatial domain. In this case, because it's a second-order equation, you will need two boundary conditions. The diagram indicates what they are. At the left boundary, t of 0 is equal to t1. At the right boundary, TL equals t2. The next exercise is about degrees of freedom. Here is a simple set of linear equations and three unknowns. Solve these equations to determine the values of x, y, and z. Pause the video now. Did you find a solution? You cannot, because there are only two independent equations. Equations 1 and 3 are linearly dependent. You'll get equation 1 if you multiply both sides of equation 3 by 2. But you need three independent equations to solve for all three unknown variables. In this case, since we have three unknowns and two independent equations, the number of degrees of freedom is 1. 3 variables minus 2 equations. That means we have to specify one of the variables before we can solve the system. Specifying one variable reduces it to a system of two equations in two unknowns. Now, have a think about what variable you can specify. What are you allowed to specify and why? Pause the video now. Okay, did you figure it out? First, throw away the top equation as it is just the same as equation 3. This leaves us with two equations. Let's first try to specify x. You can see that we will get into trouble because the terms involving y and z are the same in both equations, while the right-hand sides are different. If you arbitrarily specify x, then we'll get two equations that are y plus 2z equal different right-hand sides. So for example, set x equal to 0. Now you get the two equations at the bottom, and they both cannot be true. There is no solution, so we cannot specify x. Now, let's look at a simple chemical engineering problem. We have a buffer tank with a mass m of liquid. It is being filled at a rate F in and drained at a rate F out. The height of the liquid in the tank is h. We can write a relation for the outlet flow rate if we assume gravity-driven flow. This is that the outlet flow rate is proportional to the square root of the height of the liquid. Then we have the following model for the buffer tank. Perform a degree of freedom analysis and work out which, if any, variables you can specify. Pause the video now. You should hopefully have calculated that there is one degree of freedom. There are 4 unknown variables: m, f in, f out, and h. The liquid density ρ, tank cross-sectional area A, and alpha are parameters. Since there are only 3 equations, we need to specify one variable to solve the system. However, not all of the variables can be specified arbitrarily. Let's see why. Note that because this is a dynamic model, all of the dependent variables are functions of time. So if we need to specify one or more variables, what we have to specify in general is functions of time rather than single values. First, try specifying f out. Since this is a dynamic model, f out should be able to be specified using any arbitrary function of time. This means that it could involve discontinuities. So again, any function of time should work, including discontinuous ones. Now let's see what would happen if we choose a discontinuous function for f out. Well, f out is directly related to h through the third equation. Then h is directly related to m through the second equation. That means that if f out is discontinuous, then so is m. But this cannot happen because if it were true, then the derivative dm over dt would become infinite. That means none of f out, h, and m can be specified arbitrarily. So let's hope that the last variable f in will work. Again, f in is a function of time because this is a dynamic model. What if f in is discontinuous somewhere? This means that dm over dt will be discontinuous, but that's okay. The derivative of m with respect to time is the slope of the function m of t. The derivative of m can be discontinuous while the function m of t remains continuous. So if m is continuous, then so are h and f out. There is no dependent variable becoming infinite. Therefore, there is going to be no ill effects of specifying an arbitrary function for f in. So f in is the variable that we must specify. We can use this to derive a simple rule to help us choose the right variables to specify. Any variable that is inside a time derivative cannot be specified, and nor can any variable that is directly related to it. F in is an input to the system, and m, h, and f out are outputs or state variables. Recall state variables from your process dynamics and control module. This gives us another rule. Inlets can be specified, but outputs or state variables may not be possible to specify. So far, we have spoken about what types of equations can be in a model and what models can be used for. Now we end with an overall approach to help produce good mathematical models. One way is to ask questions about the modeling activity. Why? Ask why we want to make a mathematical model and what we are looking for. What questions we want to answer with it. This will help identify what features are needed in the model. What? What is it that we want to know by using the model? Write down all of the data you want the model to provide, and this will tell you the variables that the model needs to be able to predict. Which physical phenomena have the greatest effect on the dependent variables or things that we would like the model to calculate? Identify and write down the governing physical principles and equations. This will tell you which terms we need to include in some equations and which terms can be neglected. For example, if radiation is the dominant heat transfer, then we need to keep that term and maybe we can drop convection and conduction. Once you know the forms of the equations in your model, this will give you an idea what numerical methods will be suitable for solving it. Have. What do we already know? Identify the available and relevant data. This will probably be the inputs that the model will need to use to predict the outputs. Assume. Given the data available and what the model needs to predict, what assumptions can be made to simplify the model without affecting its ability to meet the required accuracy level? This is related to which? Identify the circumstances where the assumption is acceptable and make sure these correspond with the expected uses of the model. When we have built the model, we can make sure it is fit for purpose by making the following checks. Check what the model can predict, what are the outputs, and make sure these match the original goals of the modeling activity. Get the model verified. Check that no mistakes have been made in its implementation and it's doing what is expected. Validate the model. Check it against experimental data or other validated models. Ensure that it is predicting with the required accuracy. Improve. Can we improve the accuracy of the model by getting better estimates of the parameters? Are there any input variables that could have been missed, or are some assumptions not valid? Use. Consider again how the model will be used. Does it need to make fast predictions, for example, for online control applications or real-time operator training? Or do you need accurate predictions and you don't mind waiting longer for a more complex model to solve? The overall procedure for developing a mathematical model is as follows. You can follow this procedure step by step every time you develop your process model. Step 1. Draw a sketch of the system to be modeled. Label the various geometric, physical, and chemical quantities on the sketch. Step 2. Introduce justifiable, simplifying assumptions. Step 3. Identify the dependent and independent variables. Step 4. Establish a control volume for a lumped or differential element of the system to be modeled. Draw it on the sketch and indicate all inflow-outflow paths. Step 5. Formulate the conservation laws over the control volume. Set up the mass, momentum, and energy balances as necessary. Define the fluxes across the control volume boundary. Step 6. Define source terms in the balances, such as the reaction rates. Step 7. Check equations for consistency of units, or dimensional homogeneity. Step 8. Write down all the possibilities for boundary values and initial values for the dependent variables, and then choose the most appropriate boundary conditions for the problem. And finally, identify solution methods for the mathematical model. I hope this lecture has given you a good overview of how we can build mathematical models of chemical and other processes using a systematic approach. To summarize what we covered, we talked about what a model is and what models can be used for. We described the model development cycle, how to go from observations of physical phenomena to mathematical descriptions, and how models need to be tested against experimental data to ensure they are predictive to the required level of accuracy. Once that's done, we can use them for a number of useful purposes, such as simulations or operator training, and optimization studies that you can use to design the equipment to get the best performance. Looking at the modeling itself, we discussed the system boundary, which surrounds everything you want or need to include in the model, and what the control volume, the volume over which you write your balance equations, should be. If the control volume is the same as the whole system, then you have a lumped model where none of the variables depend on spatial position. If you have a differential control volume inside the system boundary, then you have a distributed model where the variables can depend on spatial position. We covered the types of equation that could appear in a mathematical model. Algebraic equations, so no derivatives. Ordinary differential equations, with derivatives with respect to only one independent variable. And partial differential equations, with derivatives with respect to more than one independent variable. These equations could be linear or nonlinear, the latter being much harder to solve than linear equations. And we also discussed the difference between dependent and independent variables. In addition to the equations themselves, we also saw that you need initial and/or boundary conditions in order to solve differential equations, and these are an important part of the model. Lastly, we covered some general techniques for developing mathematical models.